Hello again. Today I want to show you a very simple example of how we can use the principle of work and energy to solve for velocity of a block here. So here we have this block whose mass is 2 kilograms, and at position A, where it's attached to a spring, linear elastic spring, the velocity is 0, so it starts from rest. And then it moves to a new position, say position 2, under the action of a constant force. Let's say this force is 200 newtons, and its magnitude is constant. Okay? So when it reaches position 2, now position 2 is where S sub B is 0.15, so basically 0.15 meters, so it's going to go halfway up of the 0.3. So the spring is initially undeformed. The spring there is attached to block, and there is no friction. So we are neglecting friction. And our objective is here to find velocity as it reaches point B or position 2. So spring is attached to the block, initially undeformed, no friction, starts from rest at position 1, under the action of a constant force of 200 newtons, goes up a distance 0.15. What is the speed of the block, the 2 kilogram block at that instant? Okay, applying principle of work and energy. We know that work is equal to change in kinetic energy. And then if we try to formulate this, there are several forces here that do work, namely the work of the external force. Now we know the force is constant, but because this angle keeps changing here, right? Therefore, we have to integrate. And I'm going to show you actually that we're not going to do that. We'll look at an easier way. Then we have the work of gravity, which would be the weight of the object times the vertical displacement. And since we're going from position 1 to 2, the block goes against gravity, the motion is against gravity, that work is going to be negative. W here is the weight, Y is the vertical displacement, which would be 0.15. The work of force of a spring is simply determined by minus 1/2 K S2 squared minus S1 squared, deformation of the spring at position 2 minus deformation of the spring squared at position 1. And that's equal to, and so that's it in terms of forces, equal to change in kinetic energy, so 1/2 mv2 squared minus 1/2 mv1 squared. Now, initial velocity is 0, so no initial kinetic energy. So if you guys have seen the video prior to this related to work energy, and you can do just a simple search, principle of work and energy under my name, you'll see that I've shown in that video specifically a situation like this. Something like this, where we have a constant force, we can avoid integration and just set the work of that force into simply the simple definition of work, which is force times displacement. By D, I mean the distance that a point on the vertical, part of this cable will go through as block goes from position 1 to position 2. And the way we find that distance is very easy, and again, you can refer to that video. If you figure out the length of the cord initially, L1, and then find the length of the cord, L2, at position 2, D actually happens to be L1 minus L2. And then just using the geometry, you could see that L1 is the square root of 0.3 squared plus 0.3 squared, which becomes 0.4, sorry, 0.4243 meters, and L2 similarly would be square root of 0.15 squared plus 0.3 squared, which will be about 0.3354, and then the difference of these two, L1 minus L2, becomes 0.0889 meters. So actually the work of this force then would be 200 times this number, 0.0889. And that way we avoid integration. So now the rest of it is just a plug-in. Let me go to the next page. So we have the work of this force, which we just already simplified to F times D. Let me rewrite the equation: minus WY minus 1/2 K S2 squared minus S1 squared. You already know that initial kinetic energy is 0, so we just have the final kinetic energy here. Okay, let's plug in 200 times 0.0889. W is the weight, so it's 2 kilograms times 9.81, right? Times the distance is 0.15, that's how much the weight is displaced, minus 1/2 K. K, if you look at the next page, or the previous page, K is 100 newtons per meter. This stiffness is given. And S1, remember the spring is initially undeformed, and S2 is, again, the 0.15. Remember the spring is attached to the block. So equal the right-hand side 1/2 to velocity squared. So if you do the calculations, the left-hand side we should get 13.712 joules of energy, positive energy, equal velocity squared, and then velocity becomes 3.7 meters per second. So again, I advise you to look at the video that I had before this to see how in the case of integration you could avoid doing that for as long as the magnitude of the force is constant. Again, thank you for listening and watching.